Good morning, everyone.
Good morning.
Hope y'all had a good weekend. Any questions over anything? We're all good? Okay, well, in that case, let's get started. We're gonna finish up 7.1 today, and we're gonna get into 7.2. So we were talking last time about how we can use the integral to find the area between two curves, right? So I just want to revisit that real quick to make sure that we're all clear on the geometry that we were using. So geometrically, the idea is that we have a function that's on top, then we have some function that's on the bottom, g, and we imagine that we are going to go between some point A and some point B. And notice where we stop doesn't have to be where they intersect, okay? It can be anywhere. And we're trying to find the area in between these two. So what we do is we construct all these rectangles, an infinite number of rectangles, and we have to look at these rectangles throughout the entire area that we're considering, and we have to be sure that over the entire interval that the function that's on top is always the one on top and the one on the bottom is always the one on the bottom. And if it changes at any point, then we have to adjust for that in our integral. But the construction looks like this. If we take one of these rectangles and just imagine sliding it over to the side. Okay, so what I'm doing is I'm taking this rectangle here, this green one, and I'm imagining what it looks like if I just slide it to the side. I draw my x-axis over here, and then I talk about what the area of this one slice would be. So we try and come up with a formula for the area of one of these, right? Of one. And so the width of it, we say, is dx. That's always how much x is changing as we move across. The height of the rectangle would be that height minus this one. So that's where we get the idea of the top here, whatever that top function is, in this case, f. And the bottom of that rectangle is always dictated by the red function on the bottom, g. That's where we get the formula for this as being the area of one of these as being the height, which is the f function, minus the g function, times the width, which is dx. Is that clear to everybody, this picture in this formula? So if that gives you the area of one of them, then what you want to do is you want to add up all of them, right? And that's where we bring in the integral. So to find the true area here, we do the integral, which is basically a sum of an infinite number of those. And it's f minus g dx. Now, you'll see me say this instead. I like this formula better, actually. Top minus bottom dx. I like that more because it doesn't matter what you call the function on top. It could be f or g or h or any function. Just it's the one on top minus the one on the bottom, always. And then the width is always going to be your dx. We clear? Okay, so now we want to go backwards a little bit here and talk about college algebra. When we were defining a function in college algebra, the first time you ever hear a function, you're usually given a picture, and you're given some definition. And the definition looks something like this. A function is a rule which assigns to each number in its domain, usually we call it x, exactly one number, usually we call it y in its range. So the idea of a function is that a function takes in a number here, which we usually call x. It sends it through some function, spits it out as a new number. Sometimes it doesn't change it, but most of the time it does something to it. Spits it out over there as y. And we call that function something, maybe we call it f, right? So this is an example right here. This we would say f is a function, f is a function of x, meaning that x goes in and then something comes out, right? But x is the input. And then the function sends that x to exactly, and this is the key word in this definition, exactly one number. Okay, so again, back in college algebra, you're taught to look at these things. Like someone will give you an example. They say, what if this number went over here, this number went here, and this number went here, like that through this? Is that a function? That would be the question. And you would look at that and say, yes, because for each thing that went in, exactly one thing came out. For each input, exactly one output. Each input, exactly one output. And then they give you an example like this. They'd say, okay, is this a function? So do y'all remember, is that a function? So you have to ask yourself the question again, does each input go to one place? So does that number go to one answer? Yes, okay. Does this number go to one answer? Yes, goes there. Does this number go to one answer? Yes, there. That is still a function of x, or this is, in this case, both of those pictures are functions. The place you get into trouble is when you do something like this. Let's say that goes there, that goes there, and that goes there. See, now this is not a function, because this input here went to two different outputs, and that violates being a function, right? So here, if these are x's, then going from here to here, this is not a function of x, because it violates that every input goes to exactly one place. Now, let me ask you a question. If these things on the right are the y's, and these are the x's, oops, yeah, I'll just keep that. Then this is definitely not a function of x. But could you look backwards the other direction and look at this from right to left as a function of y? So if you look at these as your inputs, do they all go to exactly one place? They do, right? So we want, the whole reason I'm talking about this is from here on out, if somebody asks you to look at something and asks you, is it a function? You can't answer that. You have to immediately reply to that question with, well, do you want me to look, is it a function of x or is it a function of y? I have to know which one you want me to consider the input, all right? Normally up to this point, we always look at it as x is the input, x is the input, x is the input. So we're never looking at both scenarios until right now. Now we have to really make sure we understand which is our input variable. And then we can answer the question about whether or not we have a function. So I'll give you a specific example. Let's say we take this equation, y equals x squared. Okay, so the first question is this, is y a function of x? In other words, if I give you an x, can you tell me what the y is? And will there only be one answer? So think about it. If you plug in a value of x here, are you going to be able to tell me what y is? Okay, is it ever the case that you plug in a value of x and get two outputs? No, just plug in a number, 2. Okay, 2 squared is 4. Okay, that's one output. Plug in number 0. 0 squared is 0. You get one output. Plug in any number you want, square it. It's going to be one answer, right? Make sense? So this is a function of x. Yeah, yes, y is a function of x. Now, how about the other way around? Did I say if? I put if. It's Monday, I'm sorry. Is what I meant to put there. Is x a function of y? That's a question mark. Okay, I'm dragging ass today. Is x a function of y? So same equation. So what we need to do here in order to answer this is we have to take that equation, we have to solve it for x. So to solve that for x, I have to take the square root on both sides of the equation. And any time that you introduce the square root on both sides of an equation, when you actually do that mechanical process, you have to do plus or minus. Okay, so we're doing plus or minus. And so we get plus or minus square root of y equals x. Now, is the x a function of y? If I plug in a value of y, is it going to spit out something? Like if I tell you plug in 4, are you going to give me an answer? 4 for y? So if y is 4, are you going to be able to tell me what x is?
Yes, sir.
What is x going to be? If y is 4, what's x?
Plus or minus 2.
Plus or minus 2, right? That's 2 answers. That means you had an input that went to 2 different places. If y is 4, it's going to tell you that x is either 2 or x is negative 2. See, that's not going to work, right? That's not a function. That fails. Does that make sense? Now, if you look at the graph of these, if you look at the graph of y equals x squared, we all know what it looks like, right? Is that a function of x? So how do we check to see if it's a function of x? What's the good old thing we do when we have the graph?
Vertical line test.
Vertical line test. As long as we don't hit the graph more than one time, then we'd say it is a function, right? What I want you to understand now is that the vertical line test is what we use to check to see if we have a function of x. We look at the vertical line test. Now, to tell that this is not a function of y, we run the horizontal line test. If I look at the horizontal line test and I start drawing horizontal lines, if I ever hit the graph more than one time, which is happening every single time I'm doing this, then it fails the horizontal line test, which means that it is not a function of y. So does that make sense? Vertical line test checks to see if you have a function of x. Horizontal line test checks to see if you have a function of y. All right, now, why is this important? Well, let's take a look at a problem, all right? So find the, well, I should say sketch the region bounded by these curves and find the area. Okay, here we go. X equals y squared. X equals 5 minus y squared. So if you look at these, both of these curves, hopefully you recognize that both of these are not functions of x. These are actually functions of y. And if you remember back from conic sections or college algebra, you would know that both of these are parabolas that open sideways. So let's say this one right here, x equals y squared looks like this. That's x equals y squared. And 5 minus y squared, I'll do that one in red. That one right there looks like a parabola, but this one opens up to the left and it's moved on the x-axis. This is a shift to the right 5. So 1, 2, 3, 4, 5, and this parabola opens up like this. Now the region that we're looking for is this region. So what we did when we started class is we said, oh, okay, we're just going to cut that region into a bunch of rectangles and then try and identify the top function and bottom function, right? Do y'all see that that is going to be a problem here? Do y'all see that? Look, if I draw this rectangle right here, what's wrong with me saying top minus bottom?
It's the same function.
It's the same curve, right? It's the same curve on top as there is on bottom. So you can't say top minus bottom because top minus bottom would then like be 0 or something. it's not possible because they're not different, right? And then when you get over here and start drawing these rectangles, you have the same problem, don't you? The curve on top is the same as the curve on the bottom. So we can't do it this way. So what we do instead is we change the game, okay? We've always had control over how we set up our rectangles. I mean, when we first did it, we just said, hey, let's just draw these rectangles. But what's stopping us from drawing our rectangles sideways, horizontally, doing an infinite number of rectangles this way instead of the other way? See what we're doing here? If I do this, I'm going to take one of these rectangles. Why don't I just grab this one right here? I'm going to draw it down here. I'm just moving it away so we can isolate it and see it and start talking about it. Here it is. Here's the y-axis relative to that rectangle. So it's kind of like I'm redrawing this picture, but I'm just drawing the rectangle and I'm drawing the y-axis. Now, if I want to talk about the area of that one piece, right? What's the area of that one of these rectangles? Well, I need to know this distance right here, right? I need to know how wide that is. What we know though is that this red curve controls the right end of that rectangle, and we know that the blue curve controls the left end, right? But both of these, both the red and the blue, are not functions of x, are they? What are they? They're not functions of x because they fail the vertical line test. But they both pass the horizontal line test, don't they? So both of these could be looked at as functions of y. In other words, I could look at this as some function of y, and this other one I'll call it g. G, but it is a function of y instead of a function of x. And if that were the case, then if I wanted to know the distance between these two, it should be one of them minus the other one. What do you think it would be? Remember, when our rectangles were vertical, right? It was the top function minus the bottom function. What do you think it will be here? We have one on the
G of
left,
y minus f of y.
g minus f, right? So the one on the right minus the one on the left would be that distance. So for us in this one, it would be g of y, which is the red one, minus the f of y, which is the blue one, right? That's how wide that piece would be. And then how about the thickness of it? It was dx because we were moving before our vertical rectangles were left to right, right? So each little width was how much x was changing by as we moved. But now our rectangles go up and down. So what's changing this time? Is it the x or no? It's the y, right? The y that's changing. So this should be dy instead of dx. Also, we notice that we have to find where these two curves intersect and figure out not their x coordinates, but their y coordinates. And that will tell us where we're going to start. I'm going to call it C and D. Instead of A and B, I'm just use C and D. That's pretty standard. So the area of one of these, just to finish this off, the area of one of these would be g of y minus f of y, and then times dy. Now, if we want to have the area of the whole thing, we're going to add all of them up. We're going to add them all up. G of y minus f of y dy, and we're going to go from c to, I put dx there, dy is what I meant to put. So what am I saying here? I'm saying that if you have a region that's bounded by two functions of y, not functions of x, then instead of doing vertical rectangles, we're going to do horizontal rectangles. Everything's going to be in terms of y instead of x. The actual function we're going to use these, which notice we've solved for x here. So you're going to just plug those in. So everything in the integrand is going to have y in it. It's going to be with respect to y, and our limits of integration are going to be values off the y-axis. So it's like everything we did before, but in terms of y. And we will do that anytime our region is bounded by two functions of y. That makes sense? So just a slight change in perspective on things. Okay, now I like that formula, but just like I said before, I really like this formula as the one to remember for the case where we have functions of x and we're doing vertical rectangles. So to give you something similar for this, I would say integral from c to d, then it'll always be the function on the right minus the function on the left, dy. I think that's better to have that burned into your mind than it is to have like f and g and all that. It's just whichever one is on the right minus whichever one is on the left. Your integral goes from c to d, and you're integrating with respect to y. Okay. Understand? All right, let's actually do this problem. We didn't actually do it, so let me take this to a new page and we'll just finish it out. Okay, I'm gonna go. You know what? I think I'll just go grab that picture. All right, so we are going to, because we've already done a lot of this, we can at least set up the integral. It'll be the one on the right. Which one was the one on the right? Wasn't that the 5 minus y squared, right?
Yeah.
We're going to do the 5 minus y squared minus the one on the left, which is just the y squared. And then with respect to y, now we need our limits of integration. So we need to find c and d. And how do we find c and d? We find the intersection of two curves.
Set them equal to each other.
Set them equal to each other. So I'm going to set y squared equal to 5 minus y squared. So we get 2y squared equals 5. Just moving the y's to one side, divide by 2. And you'll get a plus or minus square root of 5/2. Whatever that is, you know, we could have it as a decimal or just leave it like that. But those would be our two limits of integration: negative root 5/2, oops, and positive root 5/2. And then we could do this, right? This is not a hard integral, just power rule, plug in their two numbers. These numbers being plugged in would suck. So I'd probably just do this as a decimal, just as decimals. Any questions? Sure? We'll do one more example, then I'm going to ask you to do one. So the one I'd like us to do next, same thing, sketch, region, bounded by y equals x squared, x equals y squared Yeah, let's just do that. See, this one, well, you know what? This one might be a little bit much. Let's do this. Let's change that y equals x squared to square root of x. There we go.
Isn't that the same function?
Is it? Yeah. So that's part of what this example is about.
Okay.
Is the same thing. All right. I'm going to modify it in a second. I just want to make sure we understand what we're looking at. So you have to be able to draw these things, right? That's part of this. So let's start out with, I'm going to do this one in blue. So that goes like this. Square root of x goes like that. Now, the other one in red, we know this is not a function of x, right? Because we did this earlier. And didn't we do this when we solved for y? When we solved for y, we actually had, or we did it the other way around, but if we solve for y here, we would get plus or minus the square root of x, wouldn't we? And because we have plus or minus, we know it's not a function of x. Now, is the blue one a function of x? Yes, the blue one is a function of x. It passes the vertical line test and it passes the horizontal line test. So you could look at this as both a function of x or y, doesn't matter. This one is not a function of x, and when we draw it, it actually turns out to be the positive version of this. That's right on top of it, and then the negative version of it. So it's that parabola sideways. So there is, as you can see, there is no region between these two because they are the same curve, right? They're, at least the top halves are the same, right? But the reason I want to point this out to you is that the one in red, as you see it right here, is a function of y, but it is not a function of x. The blue one, even though it's the same part of this curve, is both a function of x and a function of y, right? They're both. So let me do a modification of the red one. I'm going to just change it so that, and I'll just do it on a new problem. Let's say we're doing the curves y equals square root of x, and then the other one is x equals 1 minus y squared. So I'm going to draw these. The blue one we already did. That's just this. Right? And then the other one, I'm going to need to add one more thing here. I'm going to put x equals y. I have one more curve I added, x equals y. The second red curve is a parabola that opens to the left because there's a negative in front of the y squared, and it's been moved to the right one. So I go to the right one. I have a parabola that opens like this. And just, I think to make this more interesting, let's make this more interesting. Let's do on this y equals x, let's do negative x equals y. Let's do that. So I hope everyone understands that that's just, you know, y equals negative x is the identity function, but it's the diagonal, but it goes negative slope. So it'd be something like this. Okay, we want the region, we want to sketch the region bounded by all three, right? And find its area. So what do y'all think about that? Do y'all see the region? What's the region? Or is there an issue? Do y'all see there's two regions? Do y'all see we have this one, right? This right here. And we have this region right here. There's two, aren't there? This region and this region. Because this one right here is bounded by all three, right? That one right there is bounded by all three. And then this one right here is bounded by all three. Yes? Okay, so Let's do the green one. All right, let's just do the green one just as an exercise, because I think the green one is a good example of these sideways rectangles. Is it clear to everyone for the green one that, I'm going to get rid of the colors. Is it clear for that region right here that if we do rectangles in here, vertical rectangles would not be possible? I mean, a vertical rectangle here would be okay. Vertical rectangle here would be okay. It wouldn't be until we get over here that we have a problem, because the red curve is on the top and the bottom. So it's more efficient for us to look at this as horizontal rectangles that go like this. And now notice that no matter where I draw them, right, I'm always going to have something to the right and something to the left. Now, is the red one always the one on the right? For all these rectangles, is the red one always the one on the right? Yes? Is it always the one on the left? I mean, sorry, is the blue one always on the left? No, it switches right here, doesn't it? And then the orange one becomes the one on the left. So what we're going to need to do here is split this into two integrals. We're actually going to have two. So I would say at this point, it would be useful for us to figure out these points of intersection. And if we knew these points of intersection on the y-axis, that would allow us to see what our limits of integration are. So what would we do to find this point right here? What would be the intersection? How would we find that? What would we set equal?
Blue and red.
Blue and red. So you have to be careful here, because you can't set them equal to one another, because one of them is solved for y, the other one is solved for x, right? So how would we do this?
You make them either the function of x or you make it a function of y. But they both have to be the same.
Solve for the same. How about, yeah, I mean, that would work, but how about we just replace y with square root of x in this equation? Right? We could do that. Like write down the first equation, write down the red equation, but instead of plugging y in here, plug in what we're saying y has to be over here, which is square root of x. So square root of x squared. Does that make sense? It's like a substitution. And now when you square it, what happens when you get the square root of x squared? It's just x. Move the x to one side, the x is to one side, and you get x is equal to a half. Questions on that? So is that our answer? Careful. What do we want? Do we want the x value? That tells us where we hit here, right? On the x-axis. That point is at 1/2. Is that what we want? No, we want the y value. So if we know x is a half, now we can go back to this in yellow and figure out what the y is. So I'm going to use that to figure out that y is equal to the square root of a half. So that would be.
Would that be 1/4?
Would that be 1/4? No, that would be the square root of 1 over the square root of 2, which is the same as 1 over root 2. Then you could rationalize it if you want. That's root 2 over 2. That's about all you could do with it. You're not squaring it. You're taking the square root of it.
Yes, sir. Sorry about that.
No, it's okay. It's okay. Okay, so we know that this is, I don't know, 1 over root 2. Doesn't matter. How about this one right here? This point. Looking for the y value. We don't need to do any work there, right? If we know what the graphs look like, that's just 0. How about this last point here? What are we setting equal? We're looking at the red and the orange, right? These two. So what I would do is, Well, how would you do it? We have two equations. We have x equals 1 minus y squared. The other one is negative x equals y. And we want to know what y is, right? We want to know what the y is that make those two true at the same time. What would you do?
Substitute negative x in where y squared is.
Okay, so
So it'd be negative x squared.
okay, so you're saying let's replace that y with negative x. We could do that, yes? And we could solve that now. But remember, I said, what do we want to solve for? We want to solve for y, don't we? If we do that, we can solve it and we'll figure out what x is. And then after we get that, we go back and get y. Could we do this in one step where we are solving an equation that involves y instead of x to start?
Yeah, we would have to move the -1 over to the y, so it'd be y plus 1 for the negative x equals y, and then set them equal to each other.
So you're trying to solve this equation for y and then set them equal to each other?
So like the red and the orange, but since the orange is negative x equals y, wouldn't we have to move the -1 over?
Well, you could multiply by -1 on both sides. Is that what you mean?
Oh, yes.
Okay, we could do that, yes. Yeah, what I would do, and again, Peggy, you could do it that way, but you would just have a 2 steps to do. I'm going to get rid of this x by replacing it with something with y. And I know that negative x is equal to y, so if I just take, multiply both sides over here by -1, I know that x is negative y. And then I can replace that x with negative y. And then I have a quadratic equation in y, and so whatever answer I get is going to be my solution. Like I don't have to switch it and go find x later, or go, I'm not solving for x here, I'm solving for y. So I'll move everything to one side. Everything comes to one side, and then I solve that. I'm gonna have to use quadratic formula for that, right? Let's do that in a minute. I don't even feel like finding that answer at this point. Let's talk about the 2 different integrals we're going to set up. We have one integral here, I'm going to call it 1, and then the other integral is 2. Let's talk about that first integral. It's going to go from somewhere to somewhere, and it's going to be the right minus the left. Okay, so which is the curve on the right? Red one, right? Solved for x, which it is, so I put 1 minus y squared there. What is the curve on the left? So this is the right one. What about the left one? So what am I putting here? This is the orange one, right? Here's the equation for the orange. What am I putting in here for left then? The red one was solved
Negative y.
for x, right? Good. The red one was solved for x. So we have to do the same thing here. We have to solve for x, means make the other side negative. So this is the same as x equals negative y. So I'm going to replace that here, the left with negative y. I'm integrating with respect to y. The upper limit of integration is 0 because that's where we start. Stop. We start down here at the bottom, which is a question mark. I still haven't figured out what that is. That's this through the quadratic formula. Did anyone happen to get those solutions? There should be 2 of them. I don't feel like going through the quadratic formula. Okay, I'll do it. Y equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 1 plus or minus square root of 5 over 2. Yeah, so we have 2 answers. 1 minus root 5 over 2 or 1 plus root 5 over 2. Now, it has to be this answer. It has to be this answer right here because this one's negative and we know that we're down here. This one up here, this is actually where they hit on this back end over here. This backside, that's where they hit over there. But that's not what we're looking at. We're looking at where they hit here. So this goes from -1 minus root 5 over 2. What a mess. To 0. And that again is an integral that we could all do. I would just turn these into decimals and then just calculate. Any questions on that? We're not done, right? We need the second integral. I'm going to try and squeeze the second one in over here. The second integral is going to go from 0 to 1 over root 2. We found that earlier. It'll be the one on the right, which we already know is 1 minus y squared, minus the one on the left, dy. Now, the one on the left is a little bit weird because it's this blue one, right? Is the blue one solved for x? It is not solved for x. So you have to solve it for x. So how would you get x by itself here?
You square it.
Square both sides, right? So now you can say that the left curve is y squared. And then you figure out what these two integrals are, right? You find you calculate those definite integrals, you add up those two areas, and you would have that region. Okay, well, this looks like just a mess. Okay, I hope that you understand the basic idea here. Are there any questions on it? I'm going to go to a new page. Is that okay? You need a little more time with this, or?
I'm good.
Okay, so in a summary, if we were to summarize, we have two scenarios we can run into. We have this scenario where these are functions of x. So the blue one is y, or sorry, the y is some function of x. The red one's a function of x. The blue one is some function of x. That means that they're both solved for y. You can solve them both for y. In that case, we're going to use vertical rectangles. The integral will go from a to b. And we'll be doing the top one, which in this case would be f, take away g, the bottom one, with respect to x. The other scenario we could have is where we have x is some function of y, the blue one. The red one, x, is some other function of y. They intersect, or the endpoints are c and d respectively. We have horizontal rectangles, and then the area would be the integral from c to d of the right one, which in this case would be the f, minus the g, the left one, dy. Top minus bottom, right minus left. So anytime you can solve for y, you've got vertical rectangles. Anytime you can solve for x, you've got horizontal rectangles. All right. That makes sense, everyone? Are y'all ready to do one? I'm gonna put y'all in groups and see how y'all do with this.
So for that last equation, if we wanted to find the area of the entire thing, would we just ignore the middle, the y equals the square root of x?
Yeah, so this problem right here that I gave you initially, if you really wanted the area of the whole thing, right? If you wanted this whole thing, then you wouldn't even worry about the blue curve, right? Because you're going to wind up getting this area and that area together, which you could do in one integral. Does everyone see you could do this area in blue in one integral? The curve on the right is the red one. The curve on the left is the line. And you could go from this point all the way to that point and calculate it. Now, that's not going to happen on a test. I'm going to make sure that the region is just one region only. Okay. I was just trying to kind of throw something together real quick and didn't quite work out the way I wanted it to. Okay, where is it? We're 7-1. Dang it. Give me a moment. I have one for you to do, to look at. All right. Take a moment to copy this down. Now, I've given you the curve, all right? I've given you the curves and I've given you the region. But I would normally not give you this, all right? So write this down, just this part up here. Know that this is what it looks like, but to really test yourself on this problem, you need to see if you can get this without the picture, all right? So when I put you in breakout rooms, I want you all to talk about how you would approach this, and the pictures there just to kind of give you a hint to get you started. So for the breakout rooms, I'll put you in, you're gonna have like 3 to 4 of you in each room. And go ahead and go in there and talk to each other. I'll pull you all back here in about 10 minutes and see what y'all come up with. Okay, let's go through this, everyone. So the groups, y'all had kind of different approaches. What I want to do is start this problem as if I didn't have the graph. Because of course the graph is very helpful, isn't it? But on a test, you won't have the graph. So how would I approach this if that's the way the problem was given to me? First thing I would do is try and graph these, right? So let me start off by drawing my XY axes. And then on this first one, which I'll do in red, I need to realize that this is a function of Y, not a function of X, right? So this is basically the cosine curve drawn vertically instead of horizontally. So I'd have to know that cosine, the normal cosine curve looks like this, right? You have to know that, and starts at 1 and it goes through a period 2 pi, right? So it's the same thing, but instead of 1 on the y-axis, it's 1 on the x-axis. And then it stops here, let's say at 2 pi. Halfway would be pi. And then at the quarter marks is where I cross through. So it's going to be something like this. Yeah, that's good enough. Okay, so I need to be able to do that first. Then I need to be able to draw the same thing. This is a function of y, not a function of x. So I have to draw the sine function, which normally looks like this. Right? Starting at 0, ends at 0, halfway point. So it goes like this and back like that. Then I have y equals 0, which is the x-axis. And then I have y equals 2 pi, which is right here. Okay, so that would be my picture. Now I realize for each of these, because my regions are functions of y and not x, I know I'm going to be using horizontal rectangles in each one of them. And I should also just kind of highlight the regions. I have this yellow region. I have this green region. And I have this blue region. So when I do horizontal rectangles in the yellow region, I know that it's the red curve on the right and it's the blue curve on the left. So for this region, I know that my integral is going to be red curve, which is cosine y, minus blue curve, which is sine y, dy, because my rectangles are horizontal. And now I need my limits of integration. I know I start at 0 because that's where the bottom of that region is, but I need to figure out where I hit. So I need to know where the red and the blue intersect. And if I need to know where the red and the blue intersect, then that means I need to set the red and the blue equal to one another. And since they're both solved for x, I can set them equal to one another. So I'm just going to set cosine y equal to sine y. Had anyone gotten that yet? There's a couple of different approaches on that. I think the easiest way to solve that equation is just to think about what those look like on the unit circle. So remember the unit circle. Unit circle, our x coordinate on the unit circle is cosine of the angle. Our y coordinate is sine of the angle. So this is basically saying where on the unit circle are your x and y coordinates equal? And that happens here because we have root 2 over 2, root 2 over 2 on both. So they're both equal, or down here where they're both negative root 2 over 2, negative root 2 over 2. This angle is pi over 4, or 45 degrees, and this angle all the way around here is 5 pi over 4. So those are our two solutions, which matches up with the graph I gave you, right? So this is going to be pi over 4, which means I can throw that limit of integration on here now. So that's going to give me my yellow one. This up here was 5 pi over 4. So the green integral will go from, who wants to tell me what this integral is?
It's from pi over 4 to, or the integration is pi over 4 to 5 pi over 4.
Mhm.
And then it's sine y minus cosine y
Y minus
in relation to y.
Mhm. There we go, right? So it just, they flip places because the one on the right and the left switch places. And then the last integral, we just continue from 5 pi over 4 up to 2 pi. And we're back to like the yellow one. It's the cosine on the right and the sine on the left. And then you have to go calculate all three of those, right? And add up all the answers. So our answer is this integral plus this integral plus this integral. And that's it. Okay, I think at this point, it's all about you going and doing the homework. And so page 369, numbers 1 through 19, odds. See, that seems like not enough problems, but you know, it is what it is. I mean, if I were you, I would just do as many of those as you can, including the evens, just to get practice. I think the challenging part here is going to be graphing these things and knowing what they look like. So this is why having a graphing calculator is useful. Now, can you graph functions? Is it possible to graph a function of y on your calculator? So could you have graphed that on your calculator? That's a question. The answer is yes, you can, but you probably don't know how to do it. So at the end of class, I will show those of you who are interested how to use a Texas Instruments calculator to graph functions of y. Okay, but it'll have to be an after class thing. We are going to move on. All right, so let's move to 7.2. And we are going to talk about volumes. So we are switching gears significantly here. And I'm not quite ready. I'm not going to show you these notes. I want to just do the notes myself. All right, so we're going to talk about volumes. That's what this section is titled. So hopefully we've been talking about areas between curves. The idea of area is two-dimensional. You have a flat sheet of something. The area is how much space that takes up, right? We've always used rectangles to deal with areas, you know, length times width. And that's where we got the whole idea of like f of x dx from. But now we're going to be talking about volumes. So before we can begin, I just want to make sure we understand the basic volume formulas. So if you have like a box, like a shoebox or something, the volume of that, well, we have to know the length, we have to know the width, and we have to know the height. And if you know the length and width and height, then the volume is just all those multiplied together. We all agree with that? No one's going to argue against that, right? If you have a box, the volume is length times width times height. Now, the next shape that we need to be aware of, the volume of, is a right cylinder, a soda can, a beer can, whatever you want it to be. Okay? If you have a right cylinder, when we say right, we mean 90 degrees. I'm saying that's different than a slanted can like that. That's not a right cylinder. A right cylinder is straight up. The volume of this, well, there's a few things we need to know. We need to know how tall the can is. So that's called h, that's our height. We also just need to know the radius. And what we do is to find the volume of this is we calculate the area of the top. The area of the top is the area of a circle, and that's pi r squared. Didn't we prove the area of a circle is pi r squared? We did that, didn't we? Okay. And then what we do is we multiply that times the height. So it's almost like you're calculating the area of the top layer, and then you're just multiplying by how deep it is. And that gives you your volume. Any objections to that formula? We're all okay with that? Makes sense? Okay, the next thing I want us to be okay with is if we have a right cylinder with a certain height, and what we do is we drill out the center of this. Okay, so like we come in and we drill through that and we remove some of the volume. I'd like to see if we can come up with a formula for the volume of what's left. So if we do this, there's three things we need to know. We need to know how tall it is, which we would be given. We need to know the radius of the big can, which I'm going to call this R out. That's the radius of the outer cylinder. And then the radius right here, which I'm going to call R in. So the idea of where we're going to get this formula is we're going to say, all right, well, why don't we just look at it this way? We have the big cylinder, R out. We can find the volume of that, can't we? And then we're going to subtract from it the volume of the smaller part, the part that we drill out. That would be R in. Does that make sense as a way to come up with the volume of this thing? Just calculate the whole volume and subtract from it the volume of the smaller piece that's drilled out. So let's figure out the formula for each of these. This one would be pi times R out squared times H. Do y'all agree that that's the volume of that one? Minus pi R in squared times H. So the big difference between these two things is the R out squared and R in squared. Yes? So when we subtract those, we would get the answer. Now, both of these have a pi in them, don't they? And both of these have an H in them, yes? So couldn't I factor out a pi and an H and just be left with R out squared minus R in squared? Yeah? Okay. So that's it, right? That would be our formula. I could also write it this way. And you might ask yourself, why would you write it this way? But just bear with me. Just agree with me that there's nothing wrong algebraically with me putting the H on the back side instead of in the front. It gives you the same thing, right? I either multiply in the front or multiply in the back, you get the same answer. Okay, so these formulas are very important. I'm going to box this one. That would be the volume of a cylinder of radius R out if you drill out a cylinder from the inside that has a radius of R in. One more thing, and then we'll be ready for this. I'm going to draw a cylinder, a right cylinder, just like the one I just drew, but I'm turning it on its side. So I'm turning it sideways and I'm making it very, very thin. And I'm going to cut out a cylinder on the inside. So do y'all see that this picture is the same as this picture? I just made it very short and I turned it sideways. So if this radius from here to here, oops, from the center to here, if that's R in, and the radius all the way to the outside is R out, and this height right here I still call H, then that's still our formula, right? Like nothing has changed other than the way I drew the picture. Do you also see how it might be reasonable for me to call this a washer? Does that kind of look like a washer? When you think about nuts, bolts, washers, that looks kind of like a washer. If you don't know what a washer is, Google it. You should know what a washer is, but I don't want to presume anything, right? So it looks like a washer. All right, we're ready, right? We're ready. So what is 7.2 about? So this is everything that I just said to you a second ago, or everything we've just done. If we have a box, we know length times width times height. If we have just a cylinder, we know the volume is pi r squared times height. If we have a washer, then we know that the volume of that will be pi times r out squared minus r in squared times height. Okay, that's what all this is saying. Now, come on. Here we go. Now we get to what we're doing in here. So up to this point, we have been looking at two functions, right? Functions of x or functions of y. If it's the other, you know, if they're functions of y, we can deal with it. And we've been talking about the area between those two functions. Now what I'd like for us to consider is what would happen if we imagine that this two-dimensional picture is now sitting in three-dimensional space. So the best way for me to illustrate that is to just have you imagine that this is in three-dimensional space, right? You see that? If we were to take this region and begin to rotate it around the x-axis. So I'm rotating around the x-axis. And what I'm doing is, as I'm going through, I'm kind of like tracing out a solid object and go all the way back to the other side. I now have a three-dimensional solid, don't I? And this solid has a volume to it. I'm going to make it somewhat transparent so that you can see through. We actually have a hole in there, but it's not like a straight hole. It's not like we drilled out a perfect cylinder. This is some other shape, right? So the question would be, what is the volume of that solid? What is the volume of the solid that you get when you take the region bounded by those two functions and rotate it around the x-axis? Do you understand the question, the picture, all makes sense? So how the heck are we going to do this, right? It seems like, whoa, where do we even begin to try and come up with this volume? Well, it's actually going to be a little bit easier than you think, all right? And the reason it's going to be easier than you think is because of the idea of the integral. The idea of the integral is that it will add up an infinite number of things. You just have to figure out what it is you want to add up. We've been doing this, and that's where we started, right? And I tried to stress to you that the f of x part of it was the height of the rectangle, and the dx was the width of the rectangle. And so those two multiplied together gave you a little area of one little rectangle, and then we added them all up, right? We're going to do something similar here. We're going to look at our picture, and we're going to see if we can somehow, not illustrate, somehow, what's the word I'm looking for? Oh my God, I can't believe. It'll come to me in a second. Not illustrate, we're somehow represent the volume of that solid as a volume of a little piece of something, and then the whole volume would be all of them added up. Okay, that's the task. So if we have two curves, let's say we have this one, and let's say for simplicity, I'll just bring this one here like that. And we're not even going to have them intersect. We're just going to have them start. We're going to start this region at A and end it at B. So that way it looks very much like this picture we had, okay? If we have this and we wrap it around the x-axis, then, okay, so all we've ever dealt with is rectangles, right? So like this right here, we could find the area of that, right? Like we could find the area of that. That's not what we're looking for. But just for a second, let's put this on the outside like we had before. And I told you this part is useful later, and later's right now. I'm going to put the x-axis here, right? There's our x-axis. I also know that the x-axis I'm going to draw it in green. You can't really see it, but that right there is also my axis of rotation. I told you I want to rotate this around the x-axis, right? Later on, we're going to actually wrap around the y-axis too. So right now, our axis of rotation is the x-axis. And I'm going to draw these little half arrows, circular arrows, to let you know that we are wrapping around this axis. To the right of this, I want to draw what it would look like. So can you visualize, this is where the limitation is your brain. Can you imagine what just that rectangle looks like wrapped around the x-axis? Just that rectangle? What does it look like?
A washer?
It looks like a washer. It looks like a washer, doesn't it? My axis of rotation is down the middle. So these are three separate pictures. The first picture is the region, the two curves and the region between them. This second picture is me just kind of looking just at the rectangle with the axis of rotation. And then this third one is a picture of that rectangle wrapped. Are there any questions about the rectangle that got wrapped? Here it was, it went around the x-axis. No questions? I have another illustration that might help with that, but it's not as good. This isn't as good, this picture, because it doesn't have two functions. It just has one function on top, but I can still show you what would happen if I wrap this. If I wrap just a single rectangle, you can kind of see how it creates this. This is a washer without a hole in it, okay? This is more like a disc, but it's the same principle. Doesn't matter where my rectangle is. Also, it doesn't matter how wide the rectangle is. If I take it and I wrap it, right, then I get one little washer there, right? And what I'm going to want is I'm going to want a bunch of them, right? I'm going to want a bunch of these washers. And then I'm just going to want the number of them to just go to infinity. And if I can let it go to infinity, I'll have the whole thing. Does that make sense? So it's very much the same principle that we had with the area of rectangles, except now we're not going to be coming up with a little formula for the area of a rectangle. We're going to be coming up with the formula for the volume of a washer. So can we now discuss what the formula would be for the volume of one of those little slices, one of these washers? Well, we just said that it should be pi times r out squared minus r in squared, right, times the height. Like, that's the generic formula. Do we know any of these things?
Wouldn't
Let's
H
start-
be,
Go ahead. H, yeah, Alex, go ahead.
that be the limits of integration? The H?
H would be the thickness of the washer, right?
Yeah.
The thickness, but
So like
isn't
your
the-
A and your B?
we're not there yet. We're not adding them all up yet. The thickness of the washer, Alex, is also the thickness of the rectangle, isn't it? Isn't the thickness of the washer the same as the thickness of the rectangle? And what has that been for us? What was the width of our rectangles? What do we call that in the integral?
DX?
Dx. So we know this is still dx, right? That has not changed. So I know that the height is dx, okay? I've got that part. The other good news is that the pi is not going to change because pi is a constant. We need to know the outer radius now. So the outer radius, isn't the outer radius just the distance from the axis of rotation to the outer edge of the rectangle? Isn't it that distance right there? You'll see that? Highlighted in yellow. Isn't that the outer radius? And do we know what that is? In terms of these two functions, I never call them f and g. Here's f, this is g. So in this particular case, wouldn't the outer function just be the f function? Whatever the f is, that's how tall that is. So this would just be f of x And then what about the inner radius? That would be the distance from here to here. And what is that in terms of the functions? It's the bottom edge of the rectangle, right? Which is the g function. So that means that the volume of one washer should be pi times the outer function, which is the f function, but squared, minus the inner radius, which is the g function, squared, and then dx. Do y'all see this? This is me just applying the generic washer volume formula to a picture that we've created based on one sliver of our little function, our little region, I should say. So that's the volume of one of them. I want the volume of all of them added up, and I want to cut them up into smaller and smaller pieces. And that means I'm going to bring the integral in. So the volume will be, the exact volume will be the integral from A to B, because again, I'm going to be moving my rectangles, right? I'm going to start with rectangles on the left and go all the way to B, and then it's going to be pi times the outer radius, which in this case is f of x, squared minus the inner radius, which is g of x, squared, and then dx. There it is. And that's our formula. So again, I can't illustrate this enough to you. The formula on the bottom gives us the air, oh, sorry. The formula on the bottom would give us the area between these two curves, wouldn't it? Because that would be like top minus bottom times the width of each rectangle. That would give you the area of each of the little rectangles. You add them all up. This is the formula for the volume of the solid that you would get if you took that region and wrapped it around the x-axis. And this would work for any two functions as long as the f was on top and the g was on bottom. This would work for any two functions. So this is brilliant and amazing that this is the way we do it. But this is it right here. Okay. So let's do something. 12:30. I hate for our first example to be this example, but I don't have a whole lot of time. Next class we'll do more, but I'm going to show you just the power of this real quick. If you go look on a reference sheet somewhere and you look at a sphere that has a radius of r, if you want to know what the volume of a sphere is, you'll see that it's 4/3 pi r cubed. You can go look that up if you want. And you may have used that formula before in your life. I'm going to prove that I'm going to actually show where this formula comes from now, okay? So here's the idea. I'm going to think about a circle, right? We actually proved that the area of a circle is pi r squared. We proved that in class, like we went through the work. And the way we did it is we said, okay, we're going to look at this circle as having an equation of x squared plus y squared is r squared. And then we solved that for y. And we got plus or minus the square root of r squared minus x squared. And then we said we're only going to take a look at the positive one because the positive one gives you the top half of the circle. Do you remember me going through all that? I mean, I did do it. So if we graph just this, that gives you just the top half of the circle. Okay. So if I start with that, tell me if you believe this. If I start with that curve, but I just graph in the first quadrant. Okay, so I'm taking this graph right here, but I'm just graphing it in the first quadrant. What would happen if I wrap this graph around the x-axis? What would it create? Just imagine me wrapping that around.
A semicircle?
Semicircle. I would have half of the sphere, wouldn't I, if I wrap that around the x-axis? So if I could find the volume of wrapping this around the x-axis and just multiply it by 2, I would have a formula, wouldn't I? Okay, so that's what I'm going to do. So on this circle, this quarter circle that I have up here, I hope you all agree with me that the radius of this is r. Because we want to do this for an arbitrary sphere, so I did an arbitrary circle. So this goes to r here, that's r up here. And we know that this curve is the function f of x equals the square root of r squared minus x squared. Now, I have a region, right? I have a region right here that I'm going to wrap around the x-axis. I have a rectangle that's going to get wrapped around the x-axis. My outer radius is the distance from here to here. Do y'all agree? That's r out. Distance from the x-axis up to the top. My r in is 0. It's basically the ground. The whole time the rectangle's on the ground, so I don't have an inner radius. It's always 0. So I know right away my integral is going to be pi. My outer radius, which is this square root function, right? But what? That square root function what? Outer radius squared, right? Oh man, that's going to make my life so great. Squared minus the inner radius, which is just 0, squared dx. Now, what are my limits of integration? So be careful here. On the x-axis, where do we start? I'm choosing to start
0.
where? 0, and I'm going to stop where?
R.
At r, so I'm going to go from 0 to r. And man, do you see how great this is that I'm squaring that square root? If you go back in your notes, when we did this for the area of a circle, we wound up having to do trigonometric substitution. But it's going to turn out this can be even easier than showing the area. So I'm going to pull the pi out because it's a constant, all right? The pi is going to come out. I'm going to square the square root, which just gives me r squared minus x squared. And nothing else is there except dx. And I mean, integrals don't get any better than this. They're two separate pieces. I can do them one by one. So the antiderivative of this would be, well, remember r squared is a constant. So it may as well be the number 10, right? The antiderivative of 10 would be 10x, right? If this were the number 7, the antiderivative would be 7x. So this is just going to be r squared x minus the antiderivative of x squared is 1/3 x cubed. And I'm going to be evaluating this from 0 to r, where I'm plugging in the r for the x. Are there any questions? So let's plug r in for x. What happens? Let's see, pi. Okay, I'm going to have two different things here. If r goes in, I get r cubed minus 1/3 r cubed. So I'm just plugging in r here and here. And then I plug in 0. And when I plug in 0, everything goes away. So all I'm left with is pi. And then r cubed minus 1/3 r cubed is 2/3 r cubed. And you could rewrite that as 2/3 pi r cubed. And that's our answer. But remember, this was only half of it, right? This was only half of it. Remember, that gave us the volume of that right there. So if I double this answer, I get 4 pi r cubed. So I doubt when we walked in, well, I doubt when I started 7.2, like what, 20 minutes ago, you thought that we'd be able to prove that the volume of a sphere is pi r cubed, or 4/3 pi r cubed, right? That it would be that easy to show, but it's not bad, right? That wasn't bad at all. You know, there's a cool problem. I only have 2 minutes left, but this is a cool problem. If you take a cone, right, that has a height h and has a radius of r, the volume of this is 1/3 pi r squared times h. The way you could prove this is like this. And there was a bonus problem that I asked y'all to do that was somewhat like this. What you could do here is you could imagine that if you take that line segment right there, take this line segment, what would you get if you wrap that around the x-axis? Imagine wrapping that around the x-axis.
A cone.
You see, you would get this cone, right? So imagine this cone, the distance from here to here. If that distance is our radius, that means the distance from here to here is radius. And the height of the cone is distance from here to here, sorry, here to here. The way I would I have to work really fast here, is I would look at this as a point. This is the point 0r. This is the point h0. And because I know 2 points on a line, I can actually come up with the function, this function. It's a line. I know that the y-intercept, what's the y-intercept of that line? R, right? So I'm going to look at this line as mx plus b. I know b is r. Do I know the slope of this line? Rise over run, right? Rise over run. So if I take 0, subtract r, I get negative r. Over run, if I take h and subtract 0, I get h. That's my slope. So that is the function. I hope y'all are following. Like I said, I only had 1 minute. I'm out of time now. But that's your function right there. That is the function for this line. And now to wrap it, what I would do is pi integral. I'm going to go from 0 to h. It's going to be the outer radius, which would be the curve here, which would be that squared, minus the inner radius, which again is 0, dx. That integral will give you the 1/3 pi r squared h formula if you run through it. So a lot of geometric shapes that we know formulas for come from the idea of wrapping something around the x-axis and just coming up with the formula that way. Okay, that was a bit much. So make sure that you do your homework for 7.1. Make sure you got all that area stuff taken care of. We will do more 7.2, and I'll give you examples that are more like what you're going to see on tests. This was just to show you like the power of the volumes. That's it. I'm going to talk about the calculator. If anyone wants to stay, if you leave, you leave. You're not going to hurt my feelings. All right. So you have to have a Texas Instruments calculator for this to work, be useful to you. Let's see here. Let me open up my little emulator here. Now, before I get started, I just have to kind of preface this with this is something that you do see. Like what I'm about to show you is something that does come up in the calculus sequence. Usually when we get to it, we go through it real quick. So we're a little ahead of ourselves by doing this, but all I'm trying to do is show you a way you can use your calculator to graph functions of y that you normally can't do. So the first thing I'm going to do is just go to the y equals editor and just put this here. Let's just graph a standard function. All right. Let's just graph x squared. So if we graph x squared, boom, we hit graph, we should get our problem, right? No big deal. So y equals x squared, we're in business. The question would be, how do we graph this? How do we graph x equals y squared? That's different. See, when we type y, when we hit that button, it doesn't give us an option for this. So there's something fundamental that we have to understand before I can show you. And that is, let's start with the y equals x squared. Does everyone agree that if you look at any point on that graph, any point on this graph, the x coordinate is x and the y coordinate is whatever that x coordinate is squared. So if you plug in x is 1, you get 1 squared is 1. If you plug in 2, you get 2 squared is 4, right? So you get 1, 1, 2, 4, 3, 9, right? So whatever x is in the beginning, this is your input. X is your input, and this is the output after it goes through the function. If we look at the other one, it's kind of the backwards of that. Like the y is what goes in, and then the x coordinate is whatever that y is squared, right? So this time, this is your in, and this is your out, right? Somehow we need to tell the calculator on this that the input here is y, and the output here needs to be that input squared. But the calculator will not let us do that. Here's what the calculator will do, and this is the thing that's awesome. The calculator says, look, I will allow you to give me an ordered pair where the x can be any function of t you want, and the y can be any different function of t you want. Now, this may seem like, what? Like, what the hell is this? This is actually called parametric equations. Parametric equations. So this time what happens when the calculator does this is that you're going to give it an input. And the input that you're going to give it is t. And what your calculator is going to do with that input is it's going to create an output. But the output is not going to be a number. It's going to be an ordered pair. The first part of that ordered pair will be some function you give it for t, and the output will be some other function you give it for t. Let me give you an example, all right? Let's say I wanted to use my calculator to do this. Then here's what I would do. I would say, hey, I want the x coordinate to just be t and the output to be t squared. Do y'all see that your calculator will say, all right, for the x, I'm going to plug in, let's say 1, and for the y, I'm going to plug in 1 squared. Or I plug in 2 for the t here, the x will become 2, and the y will become 4, yes? The thing that's changed is that this ordered pair no longer represents your input and output. It represents just the output. The input is t, which is not part of your graph. So how would we do this one? Maybe you're catching on to this. Maybe you're not. How would I create that using the parametric?
T squared and then t.
T squared, then t. So now it's going to do the reverse. It's still going to plug in a value of t. This is going to be t, and that's going to be t squared. All right, so let's get to it. All right, let's get to it. I'm going to show you the calculator. First thing you need to do is go to mode, and you need to switch your calculator from function mode to para mode. There's 4 modes. You can do functions, parametrics, polars, or sequential stuff. I'm going to go to parametric. I'm going to hit enter. And now I'm going to hit y equals again. And this time what you're going to see is that instead of saying y, right, y1, y2, y3, it says what's x1, y1. So it's asking you to look at, let's do this one right here. It's saying this one is x1 and this one is y1. So what you need to do here is just for x1, we're going to put t, which just hit your variable key. It should put a t there. And then move down and put t squared on the next one. And then hit graph. And when you graph it, you should probably just see the right side of the parabola. It should be missing the left. Now, the reason why it's missing the left is because most of the time that we use parametric curves, time is in the background, like t is a background variable that you don't see, it's like time. And a lot of times we're using trig functions. So by default, the calculator by default starts t at 0 because it's like time usually, and it goes to usually 2 pi. So if you go to window, you'll see where the t min and t max is set. Change that to -10 to 10. And then regraph it, and you'll get your whole parabola. Now, the beauty of this is that if you go back to y equals, let's just leave that one there, and let's reverse it now. For x2, y2, let's do the t squared as the x, and then the t is the y, and graph it. And now you're going to get your sideways parabola. Make sense? So let's do this. We had these earlier. X equals cosine y, x equals sine y. Let's talk about what each of those, what the parametric equation forms of those would be. They're both functions of y, right? Anytime you have functions of y, your y coordinate's always going to be t, always. The x coordinate is just that function up there with t in there for y. So it's going to be cosine t. This one will be sine t. And we plug them in and go. So I'm gonna go back up here. I'm going to change these. The x will be cosine t. The y will be t, not t squared. On this one, it'll be sine t, and the y will be t. And I should graph, and I should get those functions going up. What do y'all think? Pretty cool? So in theory, okay, in theory, you never need to switch back to function, ever again. You never need to change your mode back to function, because if you wanted to just go back to old school graphing, like let's say you wanted to graph this, right? That you could type in the old way. But if I want to do it using parametric, this is a function, this right here is a function of x, right? So I would just put t here, and then this second part would be the square root of t squared plus 1. And if I do that, I would get the same thing as if I would have done it the other way. Does that make sense? I'm using the parametric mode as like a more universal way of graphing things. Any questions? One more thing I
How
want to
would
show
you
you.
graph asymptotes?
Pardon?
How would you graph asymptotes?
What do you mean?
Like, or like a regular line or something, like y equals 0 or y equals 2.
Okay, let's say you want to do y equals 0. Okay, so y equals 0. Then you would do, well, okay, so is this a function of x? It is, right? It's a flat line that passes the vertical line. So t is going to be whatever. Let's do something easier, something that we can see. Y equals 4. That when we graph it, it's not the x-axis. Y equals 4. That means the x coordinate can be whatever it wants, but the y coordinate has to be 4. So if I go over here and I say, let me clear this. If I say the x is going to be t, and the y coordinate is just going to be 4, and I graph that, I need to zoom out. There it is. Oh, it changed my damn window on me. Okay, -10, 10. There's a way to reset those defaults so that they don't do it. There it is. See it? Now check this out. What would happen if I did this? 4t. Wouldn't that give you, if I go 4 here this time, 4 here this time, and leave the y as t, graph, vertical line, right? Vertical line. What if you want to graph the line y equals 3x plus 1? Then you're going to go t, 3t plus 1. Make sense? Now, the thing that's great about these parametric is this. We all agree, I think we would all agree, that a circle is neither a function of x nor a function of y. It passes both, I mean, it fails both the vertical and horizontal line test, right? However, we also know that every point on this graph can be written as cosine t sine t, where t is the angle, right? And since t, with parametric, t is in the background, it's not part of our graph, I can use that. Let me clear all this out. It's so hard to use this without being able to clear. Okay, let me go back up. If I put here cosine t for the x and sine t for the y, t is like a clock in the background. It just drew me a circle. Now let me change my window back to 0 to 2 pi. 0 to clear 2 pi, and let me go graph again. See how it drew me that? Let me zoom, square 5. Zoom in. There it goes. Just drew me a circle. Do one more thing. I'm going to put a t in front of this. T times cosine t. And then on this next one, I'm going to go t times sine t. Watch this. Okay, let me graph that. Y'all see what that's drawing? It's kind of hard to see it. I'm going to zoom out. See what that's drawing? Drawing a spiral. Because when you think about this, t cosine t, t sine t, the t out here actually, you may or may not know that t is actually the radius of the circle. So if you had 5 sine t, or sorry, 5 cosine t, 5 sine t, you'll learn this later. This will draw you a circle of radius 5. When it's just cosine t sine t, it draws you a circle radius 1. But if I make the thing in front also dependent on t, it's trying to draw a circle with the radius that's getting bigger. And so it draws me a spiral. So the great thing about parametric curves is that you can draw things that move around in two-dimensional space in a manner that's not like a function, which in the real world is important because a lot of things in the real world, like let's say you're trying to, let's say, this is kind of a bad example, but let's say that you have a vehicle, like you're looking down, here's a car and it's driving around, and let's say you want to drop a bomb on it, right? I mean, we like doing things like that. So we want to drop a bomb on this car. Well, all the calculus that we have deals with functions, right? They have to pass the vertical line test. Well, if this vehicle is driving around doing some weird things, right? But your math only works on things that are functions. Well, this curve that it's tracing through space is not necessarily a function of x. But there is a parametric curve that goes with this. And it turns out later we can do all the calculus that we've been doing, you can do it with parametric curves also. And so it becomes more powerful to use parametric curves instead of standard functions. There's ways to draw things that go like, I don't know if you've ever seen these curves that draw like petals of a leaf like this. You can actually find the area of this thing, even though it's not a function of X or Y. There's ways to find areas. And then what you do is in Cal 3, you completely step out, and instead of requiring your object to be in 2-dimensional space, you go to 3-dimensional space. So now your object can travel in any path in 3-dimensional space. Let me show you. I'll finish up. Give me one more minute. Hold on. I can't remember what chapter it is. Vector functions and space curves, 10.7. So you have something like there we go. So here's a 3-dimensional curve, and you're right, that's a curve in 3-dimensional space. And you have this is the parametric representation of it basically, but it's 3-dimensional. So you have cosine t, sine t, and then a third component. So you're drawing this. So as the clock starts, you start moving along this curve. Okay. That's basically what's happening. Does that make sense? 3-dimensional. And we start talking about derivatives and let's see, here we go. And so why would this be important? Well, let's say you have two cylinders. Those 2 cylinders intersect, right? And let's say you need to figure out, you've got to weld this together. You got to weld these 2 things together. So you need to know how much weld this is. What's the length of that weld? Well, the first thing you do is realize that you're talking about the intersection of those curves. Then you have to get rid of those. So you need to figure out the parametric representation of those curves and then use calculus to find the arc length of those curves. And then you would know that distance, that length around. Does that make sense? But it's all parametric. See, this is the parametric representation right here of those curves. So we start doing a lot of calculus. You know, this is called a toroidal spiral. So it's, you know, yeah. Yeah, okay, so I'm getting off topic here, but we have this idea of like a tangent vector. Okay, we have tangent lines in Cal 1 and 2, but here if you have a 3-dimensional curve and you're traveling along that curve, then at every point in time, you should have some direction you're heading and a speed at which you're heading in that direction. That's called the magnitude of the vector. And yeah, so there's lots of stuff we do, but it's extensions of what we've already done into 3-dimensional space. Yeah, that's about it for that. Okay, I've gone way over. It's 1 o'clock. Hope that helped for your calculators. It's a cool thing to know how to do. So have a good one.
See you Wednesday.
Yep.